My name is Felicia Dipoko, and I like to be called AJ. My research is on the effects of processing on beta melon's ability to reduce blood sugar, its ability to have or possess its own antioxidant effect, and its sensory qualities. So this is the outline of the presentation. I'll basically introduce what beta melon is, talk about my objectives, experimental plan, and I'll run through till recommendations. So beta melon is a cucurbit vegetable. It looks like, okay, I am speaking loudly, but okay, so it's a cucurbit vegetable. It almost looks like a cucumber, but it has spikes around it, and it's been used by Asians mostly for as food or as a folklore medicine for diabetes. And several research has shown that beta melon and its extracts contains bioactive compounds that is able to reduce blood sugar and also possesses some antioxidant properties. The only problem is that there isn't much information on these reports on processed beta melon. And so this research is mainly going to focus on processing beta melon into different forms, such as freeze drying, pickled, canned, air dried, and others. And then determining whether processing affects its ability to reduce blood sugar, whether processing has that effect on its antioxidant properties. After that, we are going to evaluate the drying and water sorption behavior, because drying is an easier way for people to preserve beta melons in their homes. And so we want to identify which conditions will optimize moisture removal and also retain the anti-diabetic and antioxidant properties that we are looking at. And lastly, we're going to assess consumer acceptability on stir-fried processed bitter melon samples. Because bitter melon is characterized by its bitter taste, it's quite difficult to recommend its use for people as an anti-diabetic vegetable. And so one of the main focus of this project is to help reduce the bitterness of bitter melon by processing it. But at the end of the day, we want to know that when we stir fry it, which is the most common form of consumption among people who consume bitter melon, it's going to affect how consumers are going to accept the product. And so this is the experimental plan. As I earlier explained, fresh bitter melon slices would be processed into air-dried forms, stir-fried, pickled, freeze-dried, canned, frozen, and then blanched before frozen forms. And then we're going to we determine the antioxidants using DPPH scavenging activity and then anti-diabetic activity using an in vitro method by using alpha amylase and alpha glucosidase enzyme. And then we stir fried the bitter melon samples and then presented it to 101 panelists to determine their overall acceptability of the product. And so they rated based on the overall liking, appearance, aroma, taste, and aftertaste. Also, the air-dried bitter melon samples, because it's the most common form of drying or easiest form of drying, um, I went through the drying experiment to know which drying temperature would be best for drying to maintain its antioxidant or anti-diabetic properties. And so I'm going to take the results from the anti-diabetic and antioxidant activity first. I already went through the experimental plan, so I'm not going to go through this. Essentially, the anti-diabetic and antioxidant activity were conducted based on the methods described by these authors. The basic concepts or the basic principles of um, the anti-diabetic properties is its ability to reduce blood sugar. And we know that in digestion, carbohydrate breakdown starts from the mouth with the help of alpha amylase enzyme. And so to do this in vitro experiment, we're just going to combine starch with the alpha amylase enzyme, and it's going to produce maltose units. And when we react it with a reagent, it's supposed to produce a red colored complex. Now, in this research, because bitter melon extracts or bitter melon is known to inhibit the activity of alpha amylase enzyme, there would be fainter red colored complexes formed, just as seen here. So in the beginning, you would have an assay looking this way, bright yellow, and then when you when you heat up the reaction, you're going to have different shades of orange to reddish brown colored compounds. Sorry. Depending on the extent to which bitter melon extract is able to inhibit the activity of alpha amylase. The same principle happens in the glucosidase. So initially you would have a bright yellow solution before the reaction, and then after the reaction, you're going to see a colorless or a faint yellow to colorless color change, depending on the degree of inhibition by the alpha glucosidase enzyme. Now, all this is determined using the spectrophotometer at specific wavelengths. The same concept can be also used, or is also used in the antioxidant properties, where you have the DPPH free radical, which is purple initially, and then after the reaction, you see a pale yellow to colorless color change. Yeah. So for the results, we could tell that there was a variation in the percentage inhibition of alpha amylase enzyme by the different bitter melon samples. One interesting thing was that the freeze-dried sample retained a higher inhibition against the alpha amylase enzyme as compared to the other processed samples. Now, another thing to note is that the samples that were processed by air drying and then canning, which were thermal processed samples, essentially tend to have a lower alpha amylase inhibition. This could be because when you heat up your samples at high temperature or whilst you are canning, you tend to lose some of these important bioactive compounds. And so it explains why we would have um, a lower percentage inhibition as compared to a non-thermal processing method like the freeze drying method or even the pickling method. One interesting thing to note is that the stir-fried samples retained a comparatively higher um, percentage inhibition against the alpha amylase enzymes, even though it's a thermal processing method as compared to air drying and canning. And this could be because the stir frying method is a slow heat process, and then it's very short. And so you're going to retain more of these bioactive compounds as compared to air dried and canned product. Okay, sorry. And so a statistical analysis was run on this to determine if these differences that were observed were significant. And the p-value was less than 0.01, which is also less than our alpha value of 0.05. And so we would say that there's a significant difference in the percentage inhibition of alpha amylase enzyme by the different bitter melon samples. Now, a post hoc test was conducted to determine where these differences were coming from. Now, from this table, I'm going to run through this really quickly. there's a legend by it. So anywhere you see a yellow colored box, it means there is a significant difference. Sorry, a yellow colored or a green colored box, it means there is a significant difference. The A is the row column, and then the B is the column value. Sorry, yeah. And so when you see a yellow, it means that when you're comparing A to B, the percentage inhibition between the percentage inhibition of A is greater than B. So for example, we have A and we are comparing, say, acarbose, sorry, we are comparing without beta melon samples to acarbose. And then because without beta melon sample is in the A row, when you compare it to the acarbose, the color is yellow because acarbose had a higher percentage inhibition as compared to the without beta melon samples. So all the values that were highlighted in red and didn't have any color changes showed areas or comparisons where there were no significant differences. And so one of it was that there was no significant differences in the samples that were frozen at 20 and the samples that were blanched before freezing at 20. And so this informs us that when you want to store bitter melons by freezing and you want to retain um, the alpha amylase inhibition, you can either choose blanching and freezing or freezing at 20 degrees, and they will all give you the same effect. So with the glucosidase percentage inhibition, a similar trend was observed for the thermally processed samples. You realize that all the thermally processed samples, like the air dried and then the canned ones, had a lower percentage inhibition against the glucosidase enzymes. And interestingly, in this assay, the pickled samples had a higher inhibition against the alpha glucosidase enzymes as compared to the freeze-dried samples. And the differences observed in this percentage inhibition against the glucosidase enzymes per beta melon samples is significant. Again, the post hoc test shows you where the differences are and then where there are no significant differences. And so for the, sorry, and so for the alpha glucosidase enzyme inhibition, it was observed that the frozen sample at minus 56 degrees Celsius didn't have wasn't significantly different from the blanched and frozen sample at minus 20 degrees Celsius. Moving on to the antioxidant activity, the highest antioxidant activity from the beta melon samples was observed in the pickled samples. The first one, which is pickle 120, which is 120 ml of vinegar plus 180 ml of water in a total volume of 300 ml of the canned bitter melon. We realized that this particular concentration, or the lowest concentration of the pickled sample, had the highest percentage inhibition against the bitter melon. Had the highest DPPH scavenging activity, because we're talking about antioxidant properties here. The same trend was observed here. All the thermally processed samples had relatively lower DPPH scavenging activity. And these differences that were observed were statistically significant at 0.05. the same trend as the anti-diabetic properties. Um, the ones highlighted in red show that there was no significant difference between the DPPA scavenging activity of the product. So, for example, we have frozen at minus 56 and frozen at minus 20. They both had the same DPPH scavenging activity. After all the anti-diabetic properties and antioxidant activities, we realized that even though the drying consistently gave lower inhibition against any of the enzymes or lower DPPH activity, it is still important to look at the drying behavior and determine which drying temperature give you the best um, would give you the best sorry, would help you retain the best nutritional value, and then also help you save when you're drying, and also help you retain a lower water activity or moisture content whilst you're drying. So in the first, essentially what we did, or what I did, was to air dried bitter melon slices at 3 different temperatures. Now, in the air drying, you are going to slice your bitter melon samples and arrange them on a food dehydrator, just as is seen here. And then the moisture content and the water activity is monitored every 30 minutes whilst you're drying. And so it's going to show you how long it would take for each of the drying to complete at different temperatures. Okay. And then the moisture curves were determined from the results that were obtained from the moisture content values and then the water activity values. A sorption isotherm was also plotted to show the relationship between the moisture content and the water activity. And then the data from the sorption isotherm was also fitted in a mathematical model, sorry, 2 mathematical models to determine which one will best help or store your products better. Yeah. So in the first drying experiment, moisture content was monitored in the bitter melon slices at 3 different temperatures, which is 35, 51.7, and 68 degrees Celsius. It was observed that the temperature that was higher, which was the 68 degrees Celsius, used a shorter time to get to the critical moisture content, which is 10. So it is advised that to store dried product or dried bitter melon slices over time for a long time, you need to dry it to up to less than 10% and achieve a water activity of below 0.3. And so looking at this drying curve, we can tell that it took a shorter time for the drying at the 68 degrees Celsius to get to the less than 10% moisture content in the product. A similar trend was also observed for the water activity curve. It took a shorter time for the samples that were dried at 68.3 degrees to achieve a lower water activity below 0.3 or 0.2. Now, this is relevant in drying operations, especially if you want to conserve energy. And so you need a shorter time to dry as compared to a longer time. But we have to keep in mind that the point of drying the bitter melon slices is to keep it over time and also help to retain its bioactive compounds, which we have seen in the anti-diabetic and antioxidant graphs, that once you have once you expose the bitter melon slices to higher temperatures, you tend to reduce its bioavailability. So it is important to note that even though drying at a higher temperature helps you finish up the drying process faster. You risk losing bioactive compounds that are responsible for these anti-diabetic and antioxidant properties. Now, in this graph, it basically shows you the drying rate versus the moisture content. So it shows you the different rates of drying from A to B, which is your constant rate for drying. At this stage, the water is being removed from the surface of the bitter melon samples, and since the surface is still saturated with more moisture, it's a very slow process. Okay, it takes a while to get the water out of the food material. Yeah. And then we see another phase, which is from the B to C, which is a constant rate. And at this rate, you realize that there's a transition point and the surface water is drying up. And so the drying is more constant. Yeah. And then from the C to D is your first falling rate. In this rate, you have migration of moisture within the material to the surface, but then it's occurring at a decreasing rate. And quality of your food material is very important at this stage, which is the falling stage, because at this stage you tend to have discoloration, you tend to have heat sensitive compounds like the bioactive compounds that are responsible for the anti-diabetic and sorry, and antioxidant properties of bitter melon. You tend to lose them at this point. So it will be wise to have a lower drying temperature at this point in order to retain these compounds. Yeah. And for the D to E, it is your second falling rate, which you have water that is tightly bound. And so the rate is very slow and declining at this point. With all this, you would have to note that even though drying at 68 degrees Celsius gives you a faster drying rate, your main concern or your main focus is on retaining bioactive compounds. And so it would be important to dry at a lower drying temperature. This is the isotherm curve. It's a type 2 curve. It shows the relationship between moisture content and water activity. From this curve, we can tell that an increase in moisture content also increases the water activity. So where you have the water activity to be 1 or close to 1, you tend to have a moisture content above 80%. Now, this is important because it shows you the behavior or the interactions of water between the water activity and then moisture content. The isotherm curve was fitted in 2 models, which was the BT model and the GAB model. Now, in the BT model, only works for water activity ranges less or equal to 0.45%. And so after getting the isotherm, I fitted the results in the BT model. I had the full data, which had a maximum water activity of 0.95 for the 35, and then the adjusted data, which is the water activity that fits into the range that is recommended by the model. And so you can tell that the R squared value, which is your goodness of fit for the model in the full data set is lower than that of the adjusted data. And the highest R squared value for 35 degrees Celsius shows that it fitted best in the BET model as compared to the other drying temperatures. Now your MO value, which is your monolayer moisture content, that is 12.655 for 35 degrees Celsius, suggests that at that temperature, bitter melon retains moderate water. And so when you are going to store it, it would be prudent to have a product that has a lower um, water activity and what moisture content as opposed to those that have a higher water activity. For the G value, it shows how your how um, how water binds to the surface of your product. And so when you have a higher G value, it means you have a higher binding capacity. So looking at the results for 35 35 degrees Celsius, we can tell that it has a higher water binding capacity to the material. And so it will be difficult to lose that water or it will be difficult to lose that water, or it will be difficult for biochemical reactions to happen because that water is not available for such reactions that would lead to shelf destability. Okay, so I have a, a legend for the table that explains the individual values, like what they are, just below the table. So R squared being the coefficient of determinants, the monolayer moisture content, and then the parameter reflecting moisture binding energy for the G. Okay, so for the GAB model, which is a model that fits a wider water activity range, that is 0.95, the R squared value for the 35 degrees again was higher as compared to the other temperatures. And then the MO value was lower for 35 as compared to the higher temperatures. Now, the most important part of this table is your critical water activity, because when you have a low critical water activity, it shows that you have a lower moisture available for microbial growth and for biochemical reactions, which will lead to deterioration of your product. One thing we like to keep in mind is that we are monitoring this to be able to tell which of the drying temperatures will best retain your anti-diabetic properties or your antioxidant properties. So any of the drying temperatures that will help you have a lower critical water activity would be the best. And so in general, the drying at 35 degrees Celsius, which is lower, would be your optimum drying temperature, even though it might have high energy cost or like you have to use more time to dry. It would be the best if your target is to retain the bioactive compounds. And we can actually cross-reference this with our antioxidant and anti-diabetic property values, seeing that most of the inhibition against the enzymes were lower at the temperatures that were dried lower. And the third part of this research was the sensory evaluation bit. After processing and determining that bitter melon, yes, indeed has that ability to reduce blood sugar, we still have to target people. We still have to target the fact that it's bitter, and then we need to make it into a way that will be acceptable by different consumers. And so a sensory evaluation exercise was set up. A sensory evaluation exercise was set up. And before the actual evaluation, there were some activities that happened, which was reconstituting of the dried samples, because if you remember, I mentioned that we are stir frying the processed bitter melon samples. And so you'd have to reconstitute your dry samples, which is the air dried and then the freeze dried, before you do your stir frying. Now, in the sensory evaluation procedure, we had to get approval from the IRB board before we could run this analysis. And this analysis was actually conducted in February, so in the last week in January and in February. Yeah. The results obtained were collated, and then ANOVA was run on the results, and then AHC analysis was also conducted on the results that were obtained. From the sensory results, this is the demographic profile. So it showed that there were more male participants as compared to female participants. And then the people within the ages of 26 and 35 were higher than the other age groups in this particular sensory evaluation exercise. This is the demographic profile for the race. We realized that most of the participants were also Black or African American, and the next highest was white, followed by Asians. And then there was a question asked about people's experience with bitter melon. So we essentially wanted to determine if people or participants had ever consumed bitter melon, and it showed that most of the participants had not consumed bitter melon before. And for those who had consumed the bitter melon, we wanted to know their frequency of consumption, and we realized that even with them, most of them only consumed it once a year or less. And so it tells us that yes, even though it has these amazing properties, anti-diabetic properties, antioxidant properties, it is still not a popular vegetable. And so yeah, most people don't consume it. Yeah. And so these are the sensory outcomes for all the bitter melon samples that were served during the sensory evaluation exercise. Most panelists prefer the freeze-dried sample, and they were rated slightly above average, which is around 6, between 6 and 7 for the overall, and then the taste. Yeah. And then the other attributes hovered around the same figure as well. But I noticed, or it was observed, that most panelists liked or preserved the freeze-dried samples. So we want, in order to determine if these there were differences in the rating for the different attributes of the different bitter melon samples, and another test was conducted on the ratings, and then it was realized that there was a significant difference in the overall rating and the taste rating of the sample. So essentially, participants said, or it was determined that um, the ratings for each of the different bitter melon samples were different. But in terms of appearance, aroma, and aftertaste, participants couldn't tell any difference in the different bitter melon samples. And so if you are, or like, if you want to commercialize on bitter melon samples, stir-fried bitter melon samples, you would tend to focus more on the taste and the general acceptability of the product as compared to the appearance, the aroma, and then the aftertaste, since most of the participants here couldn't tell any difference between the different samples. A post hoc test was conducted on the overall rating and then the taste rating to tell where the differences were. So it was observed that there was a significant difference between freeze-dried sample and air-dried samples as compared to the remaining samples. But there was no significant difference between the freeze-dried samples and then the air-dried samples. This is categorized by the group letters. So for freeze-dried, you see A, and then for air-dried, you see AB. So this shows that the freeze-dried bitter melon samples were not significantly different from the air-dried bitter melon samples. And the air-dried bitter melon samples was not also significantly different from the other um, bitter melon samples, but there was a significant difference between the freeze-dried samples and then the remaining samples apart from the air-dried samples. In the taste rating, it was observed that there was a significant difference between the freeze-dried samples and then the other bitter melon samples. And it shows you that most of the panelists preferred the freeze-dried samples as compared to the other um, stir-fried processed bitter melon samples. Now, we wanted to determine where these differences were coming from. And so the data was grouped into two different clusters using the AHC test. And so this dendrogram shows you how similar each of the clusters were. So in cluster 1, you have 55 participants rating the samples similarly or almost the same. And then in cluster 2, you have 46 participants rating the samples similarly. Again, the profile for the overall liking for each of the clusters was plotted, and you can tell that most of the participants in the cluster 2 rated the bitter melon samples on the higher scale, on the hedonic scale from 1 to 9. So they were mostly around 7. The least was 6.5. But when you look at cluster 1, most of them did not like the bitter melon samples, even after they were processed. And these differences were statistically significant. And so for the different clusters, the post hoc analysis showed where the differences were. Most of the participants did not see a significant difference between freeze-dried samples, the pickled samples, and then the air-dried samples. And then the same goes for the pickled sample, the air-dried sample, and then the canned samples. And then there was no significant difference between the air-dried sample and then the remaining samples. In cluster 2, it's more different from cluster 1. We have more of the samples being similar to each other as compared to what was observed in cluster 1. The only significant differences that were observed was between the freeze-dried fresh, freeze-dried, air-dried, fresh, frozen, against the canned blanch, and then the pickled samples. After putting the participants into the different clusters, we wanted to determine what could be a factor for the ratings in each of the clusters. And so in cluster 1, we realized that most of the participants rated a lower overall rating for the stir-fried bitter melon samples, and their race distribution showed that you have more Black or African American people who are not used to consuming bitter melon, and so it's a new experience for them, as compared to Asians who happen to have that as part of their diet or happen to know that. Now in cluster 2, you have more Asians within this cluster. And so that could be a reason. It could be a reason why you have a higher acceptability in cluster 2 as compared to cluster 1. Also, we looked at the demographic influence on the clusters when it comes to consumption experience. Again, it was noticed that in cluster one, most of the participants had not consumed bitter melon before. And so you have a higher percentage, which is 78% of them saying that they haven't consumed before. And then in cluster two, you have a relatively higher percentage of them saying they have consumed bitter melon before as compared to cluster one. And this could be a reason why the participants in cluster two were more receptive of the bitter melon samples as compared to cluster one. So in conclusion, we can say that processing significantly impacts bitter melon's bioactivity, and it is statistically significant. And freeze-dried and pickling samples, which are non-thermally processed samples, best retain the bitter melon's antidiabetic and antioxidant properties. And after stir frying, the freeze-dried and air-dried bitter melon slices were more acceptable, more receptive towards the uh, more receptive by the participants as compared to the other sample. And then drying at 95 degrees Fahrenheit, which is the same as 35 degrees Celsius, was optimal for moisture stability. Some recommendations for this research is to expand the sensory trials to a broader population, since this one was to the SIE community. And so we had more people within the student population. And so maybe the next time this research could open up to the bigger Carbondale community or even Illinois State, and it will give us a better idea of how people would receive the bitter melon samples. And then further research should be also conducted on the bioactivity of the bitter melon samples after processing long term. So within its shelf life, we should be able to tell how the antioxidant properties or anti-diabetic properties are being retained or are being lost during storage. And also, we have to promote the consumption of bitter melon, particularly among African American communities, since they have a higher risk of getting diabetes, which is actually an established fact according to the CDC. Yeah.